All right. So yesterday, what we did was we started this derivation on a generalized second order system. This is going to be a underdamped system. So this is going to be a general expression for it. When we're done with this derivation, it is going to be a little bit more generalized than the textbook. Textbook will have a slightly different equation, uh, and you'll see that. So we're going to finish that up, and then we're going to move on to higher order systems, and then we will move on to lectures 5, which is going to be on chapter 6, which is stability. We covered chapter 5 already, which is block diagrams. One other thing is that I hope I have it pulled up. No, I don't. I have uploaded a practice midterm. So on under week 4, I have uploaded the midterm from last year. This is midterm 1. It should be fairly similar in scope that we will cover. It's going to be up to chapter 5. And I will upload the solutions by the end of next week. I really advise you all to try taking this and struggling, and hopefully you'll be able to do that first, then look at the solutions. Otherwise, it's going to be less effective. So solutions will be uploaded next week. Midterm is going to be on the 21st, so you have 11 days. So I'm just jumping the gun here a little bit. I wouldn't take this midterm 1 until we finish chapter 4. But basically, the way midterm is set up is that you're allowed to use a calculator, but you cannot use MATLAB or any computing software. It's open book, open notes. If you have your notes on a tablet, if you have notes on a computer, if you want the textbook on your computer, you're welcome to use that. Just be honest, don't use the internet, don't use ChatGPT. If you need to go look something up, you won't have enough time to finish this midterm. It's going to be 3 questions, 50 minutes. And yeah, go ahead and give this a shot. This is from last year. And then 3 problems. And then on top of that, at the back of the exam, I provide this reference. So like this is the inverse of a 2x2 matrix. Characteristic equation for a transfer function is this here, and then the Laplace transform tables. And this is chapter 7. You don't need that table right now, but that's also included as well when we get to chapter 7. I will probably do a review before the midterm of chapters 1 through 5 next Thursday. And there unfortunately will still be homework. I'll make homework a little bit lighter for next week. This week the homework is still like standard load, but the reason why it's standard load is because this homework is based off of chapter 4, which I think is really important. Any questions? Midterm will be in this class. Come early. I like to start early, so if everyone's here early, we can start early, get a little extra time. And for folks who are online, I'm going to just show you real quick. You're going to go to quizzes, and you'll have access to the midterm for 3 days. So from the 20th to the 22nd, you will have that time period to take the midterm and turn it in. Once you open the midterm, the timer starts. You have the allocated time to take it, and then you have to submit it online. If you want to practice what it's like, just use this feature here where I created this. And this is to simulate the midterm. And then basically the way it works is if I were to click, oh, I already attempted this. Basically down here, it says it'll let you to attempt it. And then you're going to see a timer. You're going to see a file. You download that file. That file would be the midterm. And then you need to submit that file. You can only submit once. So once you submit it once, you're no longer allowed to submit anymore. Unfortunately, there's no way to override that. So give that a try. Get your IT issues figured out before you take the midterm, and allocate your time, like allocate that around 65 minutes to take that Fast. Okay, so let's continue on with this example. So we're at the point where we're deriving the response of an underdamped second order system for a unit step input. And we're at the partial fraction expansion step. So what we needed to do next is we need to basically find an expression for we need to get this term into some form. We want this equivalent form, kind of like a s plus a squared, s plus a divided by s plus a squared plus b plus s plus a squared plus b over b. So we want this form here. Because when we get that form, we can then take the inverse Laplace transform and get, if we were to take the inverse Laplace transform of this would be e to the minus at cosine square root of bt. And this would be e to the minus at sine square root of b multiplied by t. I'm going to change this to b squared. There you go. So we want that form. All right, the first step we have to do is we have to solve for K1, K2, and K3. And for K1, what we can do is we can take K1 is equal to the limit of S going to 0 of let's see, it's going to be of S multiplied by let's see. It's going to be just this of omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. So one thing I'm going to do is I'm just going to ignore this k part and just find the partial fraction of this term here. Because all k is doing here, this big, really big k here, is doing is it's just multiplying my whole thing by a constant value. It doesn't change the values of K1, K2, and K3. Okay, so then when we do that, set S equal to 0, then we actually just end up getting 1. And to be more precise, yeah. Okay, then for K2 and K3, I just cross multiply everything. Cross multiply. both sides by s times s squared plus 2 zeta omega n s plus omega n squared. So then I get this equation. I get omega n squared. Yeah, you know what? I'll just write the whole step. So we get omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared is equal to, we know k1 now, 1 over s plus, I'll still leave k1 in there, k1 over k2s plus k3 divided by s squared plus 2 zeta omega n s plus omega n squared. Yeah, so let's multiply everything by s times s squared plus 2 zeta omega n s plus omega n squared. Yeah, that'll be more clear. So then now we get omega n squared is equal to, so then now we separate everything by the powers of s. So I get k1 plus k2 s squared plus 2 zeta omega n k1 plus k3 s plus k1 omega n squared. And so this is a confirmation that k1 is equal to 1 because omega n squared is equal to omega n squared. 2 zeta omega n k1 plus k3 is equal to 0, and k1 plus k2 is equal to 0. So then we have three equations. We know that k1 plus k2 is equal to 0 because it's the same as saying plus 0s and then plus 0s squared. Maybe I'll do a little dot here so it doesn't 0 times s. So then we can see that k2 is equal to minus k1, which is equal to minus 1. So then our second equation is this 2 zeta omega n times k1, which is equal to 1. I'll write it out. Plus k3 is equal to 0. Then we can see that k3 is equal to minus 2 zeta omega n multiplied by k1, which is 1. All right, so then we can plug this back in to the partial fraction expansion. K1 over, it's going to be k1 over s, which is 1 over s, plus k2, which is minus 1, minus 2 zeta omega n divided by s squared plus 2 zeta omega n s plus omega n squared. All right. And inverse Laplace transform of 1 over s is just 1. Now we just need to split the second one right here into the above form. So I'm going to just this is the form we want. Are there any questions so far? I'll let you guys catch up. All right, so here we have 2 zeta omega n, and when we factorize that, we can get this bottom here to be s plus zeta omega n squared, which is going to be equal to s squared plus 2 zeta omega n squared, or sorry, 2 zeta omega n s plus zeta omega n squared. And then we're missing, so then we have this extra, so we need this to equal that denominator term. So then we need to subtract zeta omega n squared and then add omega n squared. So then here, and I'll change this into a different color so we can differentiate that. So then this becomes s plus, I mean, that's not correct, but I'll just move this over. That becomes s plus zeta omega n squared plus omega n squared times 1 minus zeta squared. So basically what I did here was, this is that term here, and then this here is this term here. Maybe highlight to show that these are the matching terms. Yeah. So you're saying this should be minus s instead of minus 1? K2s, K2 minus 1. Yeah. K3 is. Oh, yeah, I see. I see. Thank you. Should be minus s. Thank you. Okay, so then now that we have at the bottom here. Yeah, that's actually my bad. It should be a square right here too. There you go. Perfect. Yeah, so then this blue and yellow highlight terms. Oops. Oh my God. I'm a mess today. I slept not a lot. I need more sleep. Yeah, yeah. But you know what's best for you, but you don't do it because you're like, well, I only have so much free time in a day, and I didn't have any free time today, so I must make up for it. So then you choose like, should I watch TV or should I go to sleep? And I ended up watching TV. I know, I know, I know. Come on, we're all guilty of it. That's why I have you guys to check my work. Sometimes I wonder to myself, why do I have to go through these derivations in class? And instead, I can just tell you all to just read the textbook. But I really don't like the algebra, but it's okay. We're in it together. I'll be better next week. I'll sleep this weekend. Okay, so anyway, So by doing that, we get 1 over s plus, and actually, I'm going to pull out the minus sign. We get s plus 2 zeta omega n divided by s plus zeta omega n squared plus omega n squared times 1 minus zeta squared. Man, unfortunately, I'm going to add another page. So now we're going to take a look at just this term only. Because we're still not done yet. And I'm going to pull this down here. Make another copy. Put it down here. This is what we're trying to achieve. So here, B is fixed. And A is fixed. We know that A is equal to zeta omega n, and that B squared is equal to omega n squared times 1 minus zeta squared, which happens to be the damping ratio. So B is going to be equal to omega n multiplied by the square root of 1 minus zeta squared. All right, so then we want this s plus 2 zeta omega n divided by s plus zeta omega n squared plus omega n squared times 1 minus zeta squared is going to be equal to s plus zeta omega n divided by this whole bottom term, s plus zeta omega n squared plus omega n squared times 1 minus zeta squared plus omega n times 1 minus zeta squared divided by this whole thing again, s plus zeta omega n squared plus omega n squared times 1 minus zeta squared. And the thing is, though, I don't think this is exactly going to be equal. What we want is we want each individual part to look like this. But most likely, we're going to have to multiply this by some gain as well for each one of them to work out. So to make this a true statement, I'm going to call this, oh man, I'm running out of variables. Let's call this, let me just use big K again. But I'm going to call this big K1 and big K2 for this to be true, because we're going to have to manipulate the numerator term to get, it's probably K2 that's going to change the most. The reason why is because we can just rewrite this term here as, we just pull out one of the terms like this. S plus zeta omega n divided by s plus zeta omega n squared plus omega n squared times 1 minus zeta squared plus zeta omega n times S plus zeta omega n squared plus omega n squared times 1 minus zeta squared. All right. So this term is done. We like that. And we need to fix this. It's not done. Are we good so far? And I'm just going to copy and paste. Sorry if you have to rewrite this again. I think yeah. So then we can see that K1 is equal to 1. All right, so then this one's, I think it's pretty straightforward. We'll just say zeta omega n is equal to K2, big K2, times omega n divided by 1 minus zeta squared. And then we get K2 is equal to zeta divided by square root of 1 minus zeta squared. There you go. So that's it. We have that term. We're done with the partial fraction expansion, and then we can plug everything back in. Any questions? Okay, so then I'm going to plug everything back in. And remember, here I took out the negative here, so I must subtract this whole thing here. And then on top of that, this whole partial fraction here is being multiplied by this constant, generic k, as well. So this is our original expression here. So just keep in mind when you do these steps, when you trace your steps, see what's being done to it. It's very easy to lose track of these things when you get stuck in the derivation, and the derivation is this long. So I'm going to write out the whole expression again. X of s is equal to k, some constant k multiplied by k1 over s, which is 1, minus k2 s plus k3 divided by that whole term, which we can actually apply a partial fraction expansion to now. We now get s plus zeta omega n divided by s plus zeta omega n squared plus omega n squared times 1 minus zeta squared minus, because we were applying the minus sign, zeta divided by 1 minus zeta squared multiplied by omega n multiplied by square root of 1 minus zeta squared divided by s plus zeta omega n squared plus omega n squared times 1 minus zeta squared. We're so close. Now we can apply the inverse Laplace transform. So take the inverse Laplace transform of x of s to get x of t. We're tracking the position of this mass spring damper system. And we get x of t is equal to some constant k. That constant k is what we pull out of the numerator to get that generalized form, multiplied by 1 plus, or 1, excuse me. Yeah, 1 minus e to the minus zeta omega n t, because that's the frequency shift theorem, multiplied by cosine of omega n times 1 minus zeta squared t, the square root of 1 minus zeta squared t, minus e to the minus zeta omega n t, multiplied by zeta divided by 1 minus zeta squared. And so you take the square root of that, multiplied by sine of omega n times the square root of 1 minus zeta squared t. That's the final expression. This is our generalized response for a second order system that is underdamped with a unit impulse. So to give you a final equation right here for a unit step input applied to an underdamped second order system, we get this. X of t is equal to your some constant k multiplied by 1 minus e to the negative zeta omega n t times cosine of your damping ratio, or not damping ratio, your damped frequency multiplied by t plus b as a function of zeta, and I'll define that. So phi is defined as the arctan, or the inverse tan of zeta divided by square root of 1 minus zeta squared. So then this term here will encapsulate, oh, sorry, I'm missing a term here. And I'm looking forward to tomorrow, Friday. It's going to be 1 divided by 1 minus zeta squared. And that's your phi term here. So basically this cosine and sine term being added together is encapsulated as an expression of cosine with a phase shift instead, because when you add cosine and sine together like that, well, in this term, we can express these two, you can consolidate these two terms and include it as a phase shift. One last thing, I mean, I already defined it earlier, but the damped frequency is omega n times the square root of 1 minus theta squared. So now that we've derived this in class, you don't have to do this on your homework. If I give you a second order system with a unit step input, all you have to do is you just need to, you can just apply it to this equation, and that's your response, forced response. The nice thing about this form, it's a little bit different from the book, is I included the K term because when your system is scaled linearly, all it does is it scales the output response in linear fashion. And if I say it's screw the unit step input, I want a 10 step input. So the input is 10. You can just pull the 10 and put it into K. So let's say this wasn't a unit step input. I said that this is a step input with a magnitude of 2, then it's just going to be 2 times K times this whole thing. Because Laplace transform and inverse Laplace transform is a linear operation, so you can pull constants out. So the book ignores the K part, and so the K is my contribution to this class. Any questions? All right, so I have some definitions on the next page here, but it's going to be the same thing as the first order system. We're going to have a rise time. We're going to have a peak time. We're going to have something new called percent overshoot. And we'll have a settling time. So all right, I'm going to just draw it out first here. So an underdamped system is going to look like this. So the underdamped second order system. It's going to look like this. We're going to have some, so we're going to have our position. So I guess in this case, it's going to be x of t. We're going to have time on the x-axis. And we're going to have our final value to be k here. The reason why it's k is because as time goes to infinity, this exponential decay term gets rid of the oscillations, and it settles at k when you take the limit as time goes to infinity. So the way the system responds is going to look something like this, where you hit this peak, and it's going to oscillate and decay. Kind of like that. Okay, so first things first, I want you to observe is that if we were to draw this decay term here, it would look something like that. That's e to the minus zeta omega nt acting on the oscillation. This point here is going to be my max point, my max value. Let me call this x max. And basically, the way we define it is that this is going to be it's called the percent overshoot. So if we have, like, let's say our final value is 1 and our maximum value is 1.5, we have 50% overshoot. So maybe I should, instead of writing percent overshoot, I would write percent overshoot. And we denote it like this: percentage sign and OS, that's percent overshoot. All right, the next one I'm going to define is the settling time. So in our first order system, settling time is defined as the time it takes for our system to be bounded within 2% of the final value. It's the same definition here, but since this is oscillating, it's going to be plus or minus 2%. And I'll do that in a different color. Let's do green. So this is 1.02K. And this is 0.98K. So basically we want the settling time to be bounded within these two lines. This is the bounds for the settling time. Well, it's not the settling time, it's the settling time value, I guess. So we would say around this point here is where it's bounded. And make space for it. Roughly here. That's TS. All right. Peak time will correlate with the maximum value. So this is the time to the first peak. And then rise time is the same definition as first order system. It's the time it takes to go from 10% to 90% of the value. Let's go with, yeah, that. So let's say this is 0.9K. And this is 0.1K. And we'll go probably there. I'm going to call this TR, which is from 10% to 90% of the final value. And we don't really look at the rise time for second order systems. We actually look at the peak time for second order systems because we want to know the maximum value. Because once we hit that value, it's just going to become smaller. We don't really care too much about rise time. I'll put one more definition. This is settling time. We want to be plus or minus 2% of the final value. And there are equations for some of these, and for other definitions, there are correlations, and I will show you that on the next page, and then we'll wrap it up for today's lecture. We won't finish chapter 4. We'll finish it on Monday. So that means you guys are safe from higher order systems being on the midterm. All right. So here are some definitions. So peak time is the time it takes to reach the first peak. Here it's defined by pi divided by the damped frequency. So this is the same as saying pi divided by omega d. Percent overshoot is defined as the exponential times negative zeta times pi divided by 1 over zeta squared. And actually, I should have a multiplied by 100 because it's a percentage. Let me fix that. So then if I were to take the natural log of that, we can get this form. You can find the damping ratio with percent overshoot. So what this is saying is when the system is underdamped, it's going to overshoot. Finally, settling time is going to be 4 divided by zeta times omega n. And then, so this is actually just an approximation. It's not exact, but I would say it's close enough. And then there's no analytical equation for rise time. Instead, they give you this graph where if you know the damping ratio, you can get an approximation of the rise time. On the y-axis, this is the rise time multiplied by the natural frequency. And then on the x-axis, this is the damping ratio. So let's say if I know the damping ratio is 0.7, I look at 0.7, and I see that the rise time is roughly 2.2. The rise time times the natural frequency. Then I divide 2.2 by the natural frequency to get the rise time. That's how you use this chart. Now, one last thing about the second order system is that I'm going to go back to the previous page. When we look at this, our second order system has two poles. So there are two poles. And they're actually a pair, or there is a pair of complex conjugate poles. The thing about this is that you can actually get a lot of information from just this pole, and we're only going to look at one of them. So this is our pole zero map, and we're looking at the imaginary and real axis. And let's say this is our pole location. This is our pole. We have a conjugate down reflecting about the real axis, but we don't really care about that. This line here, so the length of this line here is going to be your natural frequency. If I were to look at the height of it, it's going to be, it's J times omega n, your natural frequency, multiplied by 1 minus zeta squared, which is equal to J times your damped frequency. And then we would look at the x-axis. This is going to be minus omega n times zeta. So the pole is at minus omega n zeta plus J times omega n times the square root of 1 minus zeta squared. That's your pole location. So just knowing the pole location gives you information about the damping ratio and the natural frequency. Any questions? All right, so that is it for today. We will cover the midterm will cover up to second order systems. We're going to skip higher order systems on the midterm. The other thing that is included in chapter 4 is the time response, chapter 4.10 and 4.11. That's also fair game, but higher order systems, I believe section, let me go to the, 4.7, 4.8 will be left out. All right. And we can call it for today. Thanks. Have a good weekend.